upside down and inside out. About to take your education on a brand new route. Because I'm Mr. Morris and I'm here to say that it's time to teach math in a brand new way. Because if you think that your math ain't great, you're starting to hate, feel you can't relate. Well, if you know fool, be sure to stay tuned. There's a new way of learning flows into you, yeah.
Hello everyone, this is Algebra Made Simple. Welcome to today's program. Now today we're going to talk about a content standard that you'll find in both Algebra 1 and Algebra 2. It's called reducing or simplifying rational expressions. Simplifying rational expressions. So I just want to talk about what this is, unpack it in a clear, concise way, and hopefully give some clarity to much needed clarity to struggling students out there. Let's just say it that way. So first thing I want you to understand is that a rational expression, this is basically the Chris Morris definition of a rational expression. You're probably not going to see it exactly defined this way if you Google it or look up the definition elsewhere. But a rational expression is basically a fraction. Okay, so if you can reduce a fraction, you should be able to reduce a rational expression. The only difference is rational expressions are fractions that have polynomials instead of just normal numbers like you think. So for example, I'm going to show you on my little board here, and then we'll talk about some rational expressions. So if you had a simple fraction, let's take 8 over 12 for example, and someone asks you to simplify this fraction, most kids by the time you get to high school know you have to pick the greatest common factor basically that goes in between both the top and bottom numbers and divide by that number. So in this case, looking at 8 and 12, it's probably going to be 4 would be the greatest common factor. So you divide both sides by the 4, or you factor out the greatest common factor, and you're going to get the simplified form. 8 divided by 4 is 2, 12 divided by 4 is 3, and so we would say 2/3, okay, is the simplified fraction. Okay, so much like we find the greatest common factor in order to reduce just a simple fraction, it's kind of the same thinking when you're looking at rational expressions. So I want to go ahead and bring on screen a good PDF. You can probably find this one free online if you just Google search rational expressions. But if you take a look, we're going to start with this one. Now this is considered monomial over a monomial, meaning one term over one term. You notice it basically has a fraction part where you have the coefficients, right? And then you have the variable part, all right? Give it just a second. It's glitching and not responding for me. Hopefully y'all can see that. You have a fraction part, a coefficient part and a variable part. So I like to say, kids, start with the coefficient part, the big number right in front. 18 and 27, they both have 9 as a GCF. If I divide 18 by 9, I'm going to get 2. If I divide 27 by 9, I'm going to get 3. So as far as that part of it is concerned, I'm just simply doing it as a normal fraction simplifying process, right? But when it comes to the variable part, okay, the x over 6 or x to the power 6 over x to the power 4, remember when you're really using that properties of powers here at the same time. And if you remember from the properties of exponents, the properties of powers, you know that if you had the same base, x and x in this case, you are dividing them, you really keep the base and subtract the powers. So since 6 take away 4 is 2, you're just going to say x to the second power. And then this is where we would be. So this is the simplified version of 18x to the 6 over 27x to the 4th, okay? So we reduce the fraction, the coefficients, and then we remembered the quotient property of the power of exponents, all right? So zooming out of here, just kind of looking at a couple examples. Let me go down to, I don't know, maybe we'll do one that looks a little bit more fancy, right? So if you look right here, number 4 on this particular example, I'll zoom out so it looks a little more clear. You got 36 and 24, right? Well, you got to ask yourself, what's the greatest common factor that goes into both of those numbers? You have to think about it. Maybe it's 4. I mean, I know 4 goes into 36 and it goes into 24, but you don't want to be too hasty. If you give it some more thought, you'll probably conclude that 12 is the biggest thing that goes into both. 36 divided by 12, of course, is 3. 24 divided by 12 is, I don't know why it looks like that, but it's going to be 2, right? And then you're going to move on to, the variables. So a couple things you can think about. This is one of the ways I do it. If you have a variable that's the same, you got k at the top and the bottom, right? Numerator, denominator. Well, you know that essentially you're taking the difference, right? Well, 3 minus 4 is going to be a negative 1. If your bottom power is larger than the top, than the numerator, it's going to end up being a negative 1. Well, you've learned with the negative power property, it drops to the denominator. So the bottom line is whatever number is bigger, put your base and power in that spot. So if it's in the denominator, see it's k to the 4th, is in the denominator, you want to put your final answer in the denominator and keep it positive. If you look at the M's and M's, you got basically, not the candy, but M and M. You got an M at the top, an M at the bottom. 1 minus 1 is 0. It basically cancels out, right? And so if you look at the bottom, there's no other n. So the n to the power of 5, I would just leave that where it is and call it a day. Now, you don't have to have the 1 exponent next to the k because it's understood to be to the power of 1 if you just have a variable by itself, but it doesn't hurt to have it there, right? So this would be simplified to 3 over 2k times n to the power of 5, all right? And you can practice this so on and so forth in a few different ways. Feel free to rewind the video as needed, but we're going to go ahead and scroll a little bit further here because I want to look at one that's or maybe a couple, honestly, that are going to be a little more common for you guys. We're going to look at what's called a binomial over a binomial, meaning 2 terms over 2 terms, talk about how we simplify those, and then we'll talk about an example with the trinomial, okay? So with the binomials, that's 2 terms, 2 terms. You of course, kind of want to have that same school of thought where it's the GCF that comes into play. So maybe just to kind of make this a little more interactive, I'll pop my little face in there so you can see me. Okay, everyone see me good? Let's go back to it. Okay, so you look right here, you got 2x plus 6 and then 4x minus 12. Well, when you have 2 terms, if you paid attention in class, you know that you always want to look for a GCF to factoring by GCF. Between 2x and 6, the greatest thing they have in common is, of course, the 2. If you divide 2x by 2, you're left with 1x. If you divide 6 by 2, you're left with 3. So that would just come to 2 parentheses x plus 3 as far as factoring the numerator. If it comes to the denominator, you're looking at 4x minus 12 at the bottom. If you look at that GCF, well, that's going to be 4, right? 4 goes into both of those terms. 4x divided by 4 is just simply 1x, and then negative 12 divided by 4 is going to be, looks like that's going to be minus 3, okay? So if you look right here, this is going to be our first step. Now, why do we do this? Well, one of the reasons we want to factor our polynomials is to see if these binomials, right, the x plus 3 and the x minus 3, if they were the exact same thing, we could cancel the whole thing out and eliminate it in an effort to simplify the rational expression. But since this is an x plus 3, the other one's an x minus 3, we are not going to eliminate them. We're just going to leave them as is. But you see the 2 and the 4, the coefficients on the left side, that's basically 2/4. That reduces to 1/2. So you could put this simply as a 1. I don't know why in the world. Forgive me, people. That my 1 looks like, I don't know, what, Thor's hammer or something. But we're going to make that 1. Keep the parentheses x plus 3 at the top. Some people would just choose to use the x plus 3 and not have the 1 there. But the 2 would have to come at the bottom. We're just reducing the 2 over 4 to 1/2 because that's essentially the same thing. So just like you would do a fraction, that's what you're going to want to do here. So at this point, I am done. There's nothing else I can do. And there's a concept for some of y'all who might be with your Algebra 2 teachers, and a lot of times they want to talk about something called excluded values, including them. So if this video will not be covering excluded values because I want to start with the basics and do first things first, but I might do that on a separate video. Y'all let me know. So let's look at this one next to it because I think this is the best next example of something that you might see. If you notice here, this is the first one where you have 3 terms in the numerator. You got x squared plus 9x plus 20. Now, if you have not learned your factoring rules or you haven't spent a substantial amount of weeks covering all the different ways you factor binomials and trinomials, you probably want to go back and watch some of my video content on how to just factor the different types of polynomials. But once you got really good at that and you're feeling like you're proficient there, rational expressions is kind of your next step. So you got x squared plus 9x plus 20. That's a 3-term polynomial. If you remember from class, you want to find out 2 numbers that multiply, put an m for multiply, to the outside number, the 20, but those same numbers have to add to the middle coefficient. So in this case, the 9. You got to think about it. What multiplies the 20 and adds to 9? Give it some thought. I'm coming up with 4 and 5. 4 times 5 equals 20, but if I add 4 plus 5, I'm going to get 9. So those are my winners. All you have to do is put them in parentheses. X plus 4 for the 4 and x plus 5 for the 5. Remember, 5 times 4 is 20 and 5 plus 4 is 9. So that's how you factor trinomials. The bottom one is a binomial right there. You got 2x plus 8. Well, that means you probably want to factor by GCF. The GCF is 2. But if you divide both of those by 2, you're going to be left with x plus 4. Now watch this. Now you have a situation where you have 2 binomials that are the same. If you look in the numerator, you got x plus 4. At the bottom, there's an x plus 4. They eliminate each other. They're the same top and bottom. So the x plus 4s go bye-bye, and you're going to be left with what's left, which is going to be the x plus 5 in the numerator And then, of course, you'll just leave the 2 at the bottom because that didn't get canceled out. And this would be how you reduce that particular rational expression. Okay, so I'm going to just undo that so you can see my circle. I think I blocked it, but this is how you do it. So I'm doing kind of a quick rundown of the different types that you see the most, factoring by GCF a lot of times when there's 2 terms, but when you got those 3 terms, it's usually what multiplies to the outside number, like 20 here, and adds to the middle coefficient 9. Same thing if you look over here. I'm not going to do it, but there's another trinomial. So if you're factoring that one, you're looking for what multiplies the 12, 2 numbers that add to 7. I think that would be 4 and 3. So your factors, of course, would be x plus 4 and x plus 3. Then you want to factor the top one by the GCF method. So anyway, that is a quick little rundown on reducing rational expressions. Just keep in mind that reducing rational expressions is essentially, I'm going to get rid of my light there. I think I'm glaring. It's essentially a fraction, y'all. And the same way you reduce fractions, getting a GCF a lot of times, dividing by that GCF, simplifying it, it's kind of the same way with polynomials. The only difference is you got to factor, break apart polynomials the way that you've learned in class in order to find out what can be eliminated and just to give a simpler form. As I said, there is sometimes a situation where you're looking for what's called an excluded value. I'll cover that in another video, hopefully, Lord willing. But hopefully this gives you some clarity into this particular skill set. It's definitely a component of both Algebra 1 and Algebra 2. And I haven't seen a whole lot of differences between the rigor level, honestly, and a lot of the curriculum between both subjects. It just kind of pops up in both courses. So whether you're taking Algebra 1 or 2, it's still algebra at the end of the day. And this is just hopefully something that gives clarity to a lot of kids. So anyway, let me know in the comments if this is helpful or if there's any questions you have about what I laid out. If there's something that I was still unclear on, I'd love to hear your comments below so I can do a better job on my next video. As always, like, subscribe, share, click that notification bell for more content and analysis. If you like a tutoring session for your child or like to sign up for our Algebra Made Simple 10-week course, it's really good for laying a great foundation, filling in learning gaps. If you maybe got a little bit behind with the pandemic in 2020 and you're playing catch up and you got to get ready for the next grade level, it can be really good for that. So go to morrismodel.com, and book a strategy call with me today, and we'll get something set up for you and your child to be successful. I love you guys. Till the next one. I'll catch you soon. Peace.
Upside down and inside out, about to take your education on a brand new route. Because I'm Mr. Morris and I'm here to say that it's time to teach math in a brand new way. Because if you think that your math ain't great, you're starting to hate, feel you can't relate. Well, if you know fool, be sure to stay tuned. There's a new way of learning flows into you, yeah.